Thank you. My name is Roman. I'm training engineers and students in software development and system engineering. And thank you for being here. Today we're going to look into how to write software in a way that it might use more than one CPU core at a time. So who has used Go before in the audience? Please raise your hands. Okay, keep your hand up if that code used Go routines. Few hands up there, thank you. All right, this is our roadmap today, and we will be looking into two concrete examples. Do some theory first, look at the concept, how to transform an existing algorithm into a concurrent implementation. This always adds complexity, of course, but we try to keep it simple today. And in between, I will talk a little bit about Go routines. Let's have first a look. Sit back, take a deep breath and look at the hardware side of things. First, you need more than one CPU core, but nowadays this is just taken for granted. Come on. I ordered some more CPU cores here. And of course, computers are faking it a little bit. You can run as many applications at the same time as you like, and by switching very fastly between different processes, they will make the impression that this device can run as many applications as you like at the same time, but in reality, only a few will have a chance to actually run. On the software side, we start with a classic, very simple algorithm. You have some initialization going on at the beginning. Then you need to compute something, do some processing, burn some CPU cycles for a good purpose. Go to the next item, creating a loop. And after you processed all the items, you have something to show for and output the result. Now, how can we do this using more than one execution thread at a time? Of course, you have to implement your program in a different way. It won't come for free. So somehow we try to split these tasks into groups, run them on different threads so they can be distributed across CPU cores and complete in shorter time. In our first example, I will use something easy, something which is very willing to be distributed across different CPU cores. We are going to ping many hosts and try to complete as fast as possible. But let's start simple. Go already encourages you to implement something in a very simple way and only optimize after the fact, after you become aware that something needs to be improved, and then you can have a close look what to improve. Now, for this sequential algorithm, the question is how long does it take to complete these pings? And to keep it simple at the beginning, we will do everything sequentially. We send a ping to one host, wait for a response for a given amount of time, not forever, of course. And then, when we are happy with the results and we made a conclusion, we go to the next one. The time this is going to take to complete is obviously the number of hosts multiplied by the timeout you are going to apply for each single host. I use this example in interviews a lot, and over time, I received very interesting suggestions how to improve this algorithm. Let's have a look. So some people would say, reduce the number of hosts. Who in the audience would take that approach? Anyone dares? No, I see head shaking. Of course, at the end of the day, you are not done when you choose that approach and you miss some of the information you are supposed to collect. Next one would be reduce the timeout. Become impatient. Don't wait so long. But how long should you wait in the vast internet to gain accurate information? So here you are done at the end of the day, but you lose accuracy in your result. You are not waiting enough for some busy host until they respond. And then of course you could break up the sequence of this algorithm, by pinging all of these hosts at once or very quickly, and then begin to sit and wait for the responses to come back. But for my example, I don't like this. I don't like to change the algorithm. I want you to show you the simplest amount of changes that will lead to concurrent code. So today we are going for the Go routines. We are going to split this code up in order to run on multiple threads on Go routines. And to do this, we need some organizing in the beginning, firing up these Go routines. Every Go routine will deal with only one host. We try to keep it simple, remember. This is a different representation of the same algorithm. It's just emphasizing on two phases. There is the fan-out phase, distributing the tasks, and then there's the collection phase. In a consistent way, collect the outcomes of every single host and keep counters up to date. Now let's see how this is done on the console. I will start with the single-threaded, very simple implementation that I explained in the beginning. We will create variables to hold the results, and of course we have to return them eventually. And then we need some simple kind of a loop to process all the hosts, not forget one single one, and this will happen in sequence. No complication here. First, we send the ping and wait. This is all done in this one function for the result, and afterwards it returns and we can check the Boolean outcome, whether that host responded or not in due time. We will keep track of the results accordingly in these two variables and keep them updated. And this is our algorithm. I prepared a couple of unit tests to make sure after the implementation, hey, do they turn green or not? And not all of them are happy. The reason is one of the unit tests was designed specifically to check the overall execution time of this simple algorithm, and of course it detects that at the end of the day we are not done because this takes too long. Okay, so how can we transform this into a concurrent implementation? We have to somehow make that decision to fire up new Go routines and put the specific part of this existing algorithm into a new Go routine. Of course, we will choose line number 24 here because this is the workhorse. This is where the action happens. We will create an anonymous function to keep the code readable and short, and we will include the execution of the ping in that new Go routine, and also the collection of the results, but we will use a channel instead of a variable, otherwise we run into a trap. Concurrency opens a whole can of worms to run into problems. One of them is data races, and therefore we should not write into the same variable from different threads. Don't do that. So we create a channel which is specific to Go, and we will send a true value down the channel in case a host is reachable, and if not, we don't send anything. Then the collection phase, that was the fan-in phase that I showed you at the bottom of the previous slide. We have to somehow keep reading from the channel and collect the outcome. Now this will run in the main Go routine. Whenever you fire up a Go program, it will already give you the main Go routine for free. This is where your main function runs in. And our unit tests are not happy. We are running into a deadlock. Wow. This is another trap that can happen as soon as you make something concurrent. But there are means against it, luckily, and in this case we will use a wait group. We have to somehow know in line 34 when should the waiting for more results be terminated. This thing will wait forever, and it's detected by Go. This is why it aborts with an error. Okay. A wait group is basically a counter which can be used in a thread-safe way. So if you increase it, decrease it from different Go routines, it doesn't matter. It will always happen in a consistent way. First, we create the wait group, and it's being initialized with the value 0. And whenever we fire up a new Go routine to ping one single host, we are going to add 1 to the counter. And as soon as a Go routine terminates and has completed its task, at the end of the Go routine, we will call the done function, and it will decrease the counter by 1. Now we have our signal and know we can wait for this Go routine to end. And we are creating another Go routine which is only kept here for housekeeping reasons. It's very simple. It does only one thing. It waits until all the other Go routines have completed. And then it closes the output channel. And that will automatically, in line 44 by now, we added a couple of lines here, it will signal to this range out loop, you are done. There are no more things to wait for. Right. I now want to take a step back again, out from this example, and show you a common trap people that do this for the first time tend to run into. Looking at the simple program, initializing a value with 0, then firing up a Go routine, increasing the value by 1, no loop, no repetition, this only happens once, and then printing out the value. Who in the audience would expect 1 to be printed on the console when this thing is being executed? Yeah, thanks. And who would expect something else than 1? No one. Right, now what will happen here is that this Go routine will be created, but there's no guarantee when this thing will happen to run. The Go scheduler is made in a very efficient way. It's lazy. That doesn't apply to human beings. Lazy people are not always very efficient, but here the concept is only look for a different Go routine to execute if the currently executed Go routine is being blocked by something. And so we would, in this case, never force that new Go routine to actually execute, and it will show you the initial value on the console, which is 0. I can't go into details how to fix this right now, but I just give the suggestion that at the point where this arrow is pointing, you need to do something. You need to block the currently running Go routine waiting for something. You can use wait groups, but you can also use channels. If you're unsure how to use wait groups, use channels. they are blocking as well. Okay, another example with a consistency trap is this one here. This time the print is in the go routine, and we have our wait group in place, so there is blocking, no problem. We won't run through without executing this thing. But there's another problem. The output of this should show 0 and 1, because this is what X is iterating over. So I'm presuming you know something about code. And the problem is, in reality, you're not going to see that. You're going to see 2 and 2. And the reason for this is, by the time the go routine is executing, it's already too late. X already reached the termination value of 2, and this is what then eventually gets printed, because you are sharing the scope here. And what you can do is, you can simply introduce local parameters to your anonymous function and make sure that you use copies of X, and then you will be sure to use the values at the time when they were created. Good. Let's advance to the next example. This algorithm is very well known. It's a recursive algorithm to calculate the factorial, and it's not very happy to run concurrently, because in this example, every recursion depends on the next one. And only after you got back from the deep dive of recursions, then you have your result. And if you would split this up in the middle, you risk returning an inconsistent result. What we will do here is a trick. We will break up this algorithm, which I avoided with the ping example before, for simplicity reasons, but here we are forced to, and we use a mix of iteration and recursion. We will extend this algorithm to operate on a range of numbers, not the entire range, just a sub-range, not go from n down to 1, but from n to m. And we create enough of these groups, so in the end we will perform all the multiplications that are necessary, but we can do separate recursions, and each one happens on a different CPU core, hopefully. By the way, there's no guarantee for this. You have no influence on this directly in Go. This is for good purpose, because they want to keep it simple. Here is already the simple algorithm of the classic recursion. And what we will do first is rename that function. The user should use the same interface. He should not be concerned what we did under the hood to make this thing complete faster. And we will provide the same interface with a different function that will set up the Go routines for us and run these different groups separately. So here we extend the old factorial recursive algorithm, and we make it in a way that it accepts a range, an upper boundary and a lower boundary, so we don't run over the entire range. We don't want that to gain concurrency. Question is, how many workers should we create here? In the host ping example, we had one Go routine for each host. Don't be shy. Go is very efficient regarding Go routines. You can create hundreds of thousands or millions of them within no time. But for some applications, it adds more overhead, and in the end, you eat up the gain you try to have. In this case, we will say we will use a constant and create 5 workers, which reflects 5 Go routines. We need to then calculate how big will one chunk within that number range be. So this is the difference between n and m. And we will create our channel to collect the partial results. We have to combine them in the end. We will also create our wait group, so we know when all the workers have completed, and otherwise we run into the deadlock as before. And here comes the iteration part of our new algorithm. We will, for each group, run one separate Go routine. And here it comes, almost. Type safety is a huge thing in Go, which I love. We will then fire up a Go routine. Again, we use an anonymous function so we can group easily together what belongs together and have it all in one place. So here we dive into the recursion, and this happens for every Go routine separately. We need to pass our local variables for consistency, as I explained before, and we will use the upper and the lower boundaries. Of course, we have to compute them. Here, for the readability of the code, I use extra variables. You could eliminate lower without a problem. And pass these current values into the Go routine. Remember, the Go keyword does not start the Go routine, it just creates one which will be scheduled as soon as the main Go routine blocks for the first time. We send down our partial result, the channel, and we signalize in the wait group that that Go routine has completed. Then there's some edge case. You always add complexity, as I promised before, when you go concurrent, and there are always edge cases to check. No one said that the number of Go routines is a divider of n, the number of numbers we need to multiply. Sometimes they are off a bit. We have to correct for this. And now we are ready for the fan-in side, where we collect the results and we still have to multiply these partial results in order to get a correct outcome. The code as it stands here would of course block, because we are not waiting for the wait group to complete and we are not closing the channel. But we will do the same here. We will create a small housekeeping Go routine. Let's balance these brackets first. So you see the collector at the end should not be part of your Go routine. That would be a severe bug. Here we go with the housekeeping tiny Go routine, and as before, it just waits for the wait group to complete, and it will close the output channel. Never forget these empty parentheses at the end. They are important. So it's good that we have these unit tests in place, because whenever you refactor an algorithm in that depth, you are happy to verify your results and be sure that you reached an implementation that actually works. Renaming the original function had some impact on the unit tests, and we don't want that. The unit test should only test from the outside perspective of a user. It will not call the recursive function immediately. You can have that extra, but you definitely need to test these functions from the outside perspective using the original interface. And now these unit tests turned green, and we are happy, and we have our concurrent implementation of the factorial. Of course, when you use this with the unsigned integers in this example for simplicity, you won't gain much speed, because numbers have to still be kept small to fit into 64-bit numbers. You would use the big int library usually, but then this code is basically unreadable for an audience. And then you can use very big numbers. Now, if you're kind of overwhelmed and think like, wow, this was only the tip of the iceberg and there are so many things to consider when using concurrency, of course it's a journey, and you have to learn and walk through different problems and face them and learn how to solve them. From experience, I can say in Go, they make it as easy as it can be for you. In other languages, it might look easier or uglier, but they will leave more up to your sleeves to deal with, and it's a very nice concept here with these channels. So if you have questions, for time reasons, I won't take questions right in here. Please find me at the Beriflab information booth. And Beriflab offers a Career Start program for students in the last semester or for graduates in order to learn these things. And there I will be giving a system engineering course where we look into Linux, networking, cybersecurity, and also into programming, software design. Thank you.